Hello everyone, this is Jude Leonard from Department of Physics, St. Joseph's College of Arts and Science, Kadalur. Today we are going to discuss about X-ray diffraction. Before that, we have to know what are X-rays. In electromagnetic spectrum, the X-rays are categorized in the shorter wavelength region, and these are produced when there is a electronic transition occurs in between the orbitals of an atom. It means that when an electron in the inner orbit get expelled by giving out the amount of energy externally, the vacancy is filled by the another electron in the higher orbit. When this electronic transition is carried out, the energy gap between those two orbits is expelled in the form of rays, and these X-rays having shorter wavelength are known as X-rays. This shows the schematic representation of X-ray diffraction technique. An X-ray tube, that is a source, is a Coolidge tube used to produce the X-rays, and it is made to fall on a light screen or a filter which is collimated to the sample given here, and here it is a crystalline solid. Any kind of sample can be used, and we know that the X-ray is having a very short wavelength. It is nearly equal to the distance between the two lattice points, so it gets diffracted. It obeys the Bragg's law. We discuss later about it. So we get the diffracted pattern on the screen. The basic principle of this X-ray diffraction is the constructive interference that happens between the monochromatic X-rays and the sample which is placed in its path. So there is a bending of X-rays, and due to this diffraction patterns happens. So the constructive interference happens, and we get the image of that spots of the lattice points on the screen. So the basic principle is constructive interference, and this is the interaction of that source X-rays with the atomic planes, and it is very important to have that constructive interference is to satisfy the Bragg's law. And we know that Bragg's law is the fundamental for this particular diffraction phenomena. 2d sin theta is equal to n lambda, and there are three parameters. Lambda is the wavelength of the source parameter. Theta defines the orientation of the crystal, and the diffraction pattern which happens on that lattice point, within the lattice points and the source, and the angle creates over there due to the scattering effect, and it determines the angle of both coherent and incoherent scattering, both the crystal lattice and the rays which is infrared on the crystal, and d is the distance between the planes of the crystals. This is very important point in this X-ray diffraction. What is the purpose of using X-rays? The purpose is very important, because in order to get the diffraction pattern, the wavelength of the source is typically in the order of 1 to 100 angstrom units, because it matches the exact lattice spacing between the two lattice points. So in order to fulfill this particular distance, X-rays are used, and it is the wavelength is nearly equal to it, 1 to 100 angstrom units. This is why we are using X-rays as a source to happens the diffraction pattern. This shows the instrumentation part of that X-ray diffraction. and here X-ray is the source, and it is made to pass over the collimating system. So it is made to fall on the sample on the, here it is a crystal on the sample holder. So it is a rotating crystal method, so we can easily rotate by changing the angle of different positions of the sample. So there is a difference between the direct beam and the diffracted beam. In this difference makes the a clear image of that sample, the internal structure, the position of the lattice points, and there are numerous applications of this particular method. By adopting this particular method, we can computerize, digitize that photographic plate in order to analyze the various applications of that sample. The method adapted over here is rotating crystal method. A single crystal is mounted on the crystal holder, sample holder, and it seems to be the normal to the axis of a source, that is monochromatic X-ray beam, which is a source, and it is placed to the normal to the path. A cylindrical beam, as we see in the schematic representation, a cylindrical beam is placed around it, and the crystal is rotated about its chosen axis. We can rotate by a shaft on a cylindrical beam. As it rotates, a set of ladders will appear on the film on the photographic plate, so we can easily analyze the internal structure. The main aim is to satisfy the Bragg's law. Since we are using X-rays, the wavelength is so satisfying the Bragg's law, and this results in the occurrence of diffraction pattern of that particular sample. Lattice constant can also be determined by using this method. By varying the crystal orientation, by changing the rotation of the sample holder, we can determine the external phenomena such as shape, size, various unit cell parameters A, B and C. This particular methodology has a wide and various applications in various fields: chemical, biochemical, physical, in all types of material sciences. There are types in this diffraction. By changing the source of this diffraction, X-ray can be replaced by electron and neutron also, which gives further information about the sample, such as the interior structure of the sample, whether it is amorphous or a crystalline in nature, the arrangement of atoms inside the lattice points, and it also deals about the molecular level, molecular structure of that sample. And in forensic examination also, it deals with that study of that sample. In textile fibers, textile industries also, it is somewhat helpful. The average spacings between the rows, that is the crystal planes, can be easily analyzed by adapting this particular diffraction technique. The average spacing, there are a number of crystal planes, and the average spacing can be, the distance d can be analyzed or determined by using this method. The orientation of the sample, it means here if we take a single crystal for analysis, the orientation of the single crystal can be studied, the directions of the single crystal in which it is progressed, to find the crystal structure. It's so important in which category the material sample belongs to. This is the major diffraction technique used to study the structure of it. And externally we can also determine the size, shape, the defects inside the crystal, and the results of the defect, what could be the internal stress, of the crystalline region, both on the surface as well as the internal stress. We also detect the pattern of the crystal due to that scattering. When the beam strikes, there is a scattering occurs between the crystal lattice and the X-ray source, so diffraction pattern appears. From the diffraction pattern, we come to know all kinds of information about that sample. By digitalizing that spots, we can use to record and for analysis purposes. This brings some kind of outline about the X-ray diffraction, its applications and the instrumentation part. Thank you.